Speaking of which, I know this is a dead meme, guys, but I feel like I was trying to think about what we were going to make today, and I figured we would make a fidget spinner. Don't hate me for this. And it should turn out all right. I know it's a relatively simple project, but actually there are a few challenges that are going to be relatively difficult to overcome, and something that I haven't actually tried on this machine yet. And one of those things is going to be making a fixture plate and ensuring that we can hold down. I'm sure if you guys have ever seen a fidget spinner, there's basically a bearing in the center, and then there are two caps that go over that bearing that hold in the center. And so those two caps, obviously, if we had a lathe, would be relatively simple to make, but we don't have a lathe, so we're going to make them on a mill. And to be able to hold something that small is going to be a little bit of a challenge. So I'm going to give it a shot. We might break a tool, we might not. It's going to work out either way. So this is the piece of material that we're going to be making our fidget spinner around. You feel free to pass that around. That is a 6061 T6 and something else, 6221 series. So that is just your most machinable, most weldable, most compatible aluminum that you can buy. That piece is probably about $12 worth of aluminum or less.
Where do you buy it?
Huh?
Where do you buy it?
So Online Metals in Ballard, or there are a ton of other metal supply shops kind of everywhere, and you can just walk in, pick up raw material.
Have you tried metal supermarkets?
I have not.
I think you can find metal like this in a scrap bin.
Mm-hmm.
It will be like significantly cheaper.
Right. Yeah. So yeah.
But
Certainly.
you have to like dive there and dig.
Yeah. Okay, so that is, I actually didn't measure it. I should, because it's going to be necessary later on. So just get that back up here at some point. And then I have two 1 by probably 3/4 of an inch little blocks here, and these are going to end up our little caps for our fidget spinner. So this is Fusion 360. Relatively simple to use. Again, it's free for hobbyists to use if you would like to download a copy from the company Autodesk that makes it. Super awesome, pretty easy to get started. Doing more complex stuff obviously is quite difficult. So I just want to, full disclosure, I am a hobbyist. I worked professionally as a machinist for a short period of time. So I may make mistakes along the way, so just be prepared for that.
Back row hasn't seen it. Back row.
Wait, what?
Back row hasn't seen it.
Oh, back row.
Oh,
Thanks.
awesome. All right. Alrighty, so I'm trying to think about an actual design to make here, or how to, what profile to make this fidget spinner in. So I'm actually just going to start with something basic here. So everything starts with selecting a plane that you create your sketch on. So I'm actually going to start on the, so this is going to be your y-axis, this is going to be your x-axis. We're basically looking down from the z. So this is the perception that the machine would have on the part if you were looking down from the spindle. So I think I'm going to start with a center diameter circle. Now I have this bearing here, and I'm going to use a Mitutoyo micrometer here to measure this bearing, and we're going to determine its dimensions. Cool.
How much was the micrometer?
About 200.
Wow. Is it digital?
It is digital. I could have bought one with a NIST certificate, but decided not to because that was $300. But it is a digital micrometer. So, and this is accurate down to 1/100,000th of an inch.
100.
So 10 times 1/10,000th of an inch, so 10 times the accuracy or the repeatability of that machine. And
On micron.
I can't tell you. Probably submicron at that point.
Maybe like 3 microns?
10,000 of an inch is 2.5 microns.
So it's 1/1000th?
1/10,000th. So this is accurate to 1/100,000th. And we can do the conversion here in a second.
Wait a second. So it's like less than a micron.
Yeah, submicron, certainly. So the greater diameter of this bearing is 0.86580 in inches. Sorry, we're working in inches today. I guess I could go to millimeters. In millimeters, that is 21.992.
Are the bearings that consistent? Like, do you think it would be worthwhile to measure more than one? Or?
Depends on what the application is. So if you're making a skateboard wheel, you can probably take whatever the nominal dimensions from the manufacturer are or is, but for something that you want to be precise, you'd probably measure every bearing.
Okay.
Let me make sure I got this right here. So we have 0.86575. So we obviously don't need a tolerance that high. So I'm actually going to make this oversized a bit by go to 8.659. So that is our outer diameter. So this is kind of going to be the basis for our design here, because this is kind of where the bearing has to sit. It has to sit kind of at the center of mass here. So now we need some mass on the outside. So we can either do like a 3-prong fidget spinner or a 2-prong. I think it's going to be easier to hold one that has only 2 sides instead of 3, because I have a vise and it only clamps on 2 sides. If we made a 3-dimension or a 3-sided fidget spinner, I would likely have to make vise jaws that could hold it without deflecting the part and changing some tolerances for the worse. So let's sketch a center diameter circle, and let's kind of wing it. How would somebody care to measure with these calipers the distance between the tip of your forefinger and the end of your forefinger? You can give it to me in millimeters too. That's fine.
Forefinger?
Yep. This guy.
Oh, this. Okay.
I need to turn it on.
Oh, that's the 0. Hold on. 0. How much did the desk cost?
Those are cheap.
Cheap?
Cheap.
20 bucks?
I think that was about 80.
80?
And you can get Toyo ones that are
Okay.
as much as you want to spend.
Cheap is 0.
Sedan costing micrometers.
The ones
3.78 inches. Wonderful. Huh?
The ones from Harbor Freight work.
Yeah.
So, and those are
Right. They
they work until they don't.
right.
I bought ones in Harbor Freight, they don't work. Probably it's so horrible that you can't tell that it's working. But from Amazon or AliExpress, it kind of works. For the same price, $16.
So we need to stick to an overall length of under. That's probably reasonable to say under 6 inches end to end. That's a pretty large fidget spinner, actually. That's massive.
Maybe
I'm going to shrink it down a little bit. Let's do 5 inches.
It's kind of the radius.
Right.
Or, you know.
Yeah. So let's wing a little bit. Let's stick with. Let's actually go with 4.75 inches. So actually, what I'm going to do here is I'm going to create a construction line that's 4.75 inches long. I'm going to use this as kind of a guide here. So I'm going to select our line, and I'm going to hit construction here. Obviously, this is not something that's modeled. I can move this around kind of wherever I want. And then we're going to constrain this circle to this line. So I'm actually going to hit.
keyboard shortcuts for the constraints?
That's a good question. There are probably for some.
You just gotta, it's probably a lot of keyboard shortcuts.
Right. So we're going to. Where is the constraint that I want? Where are you?
Yeah, that's probably the one.
Coincident?
Yeah, you want to put the center on the line, right?
There you go.
Yeah.
Perfect. So, and then we probably want a midpoint. There we go. And we stop sketch. So we have this exactly centered. So everything kind of needs to be within this size. So we can continue to model here. I'm actually going to make another circle, and we're going to use probably a 2-point circle. And let's see how large we can make this. That's a little large. Let's stick with about a 1.25 inch. Cool. And I'm going to copy this guy, and I'm going to move it over here. Stop sketch again. I'm going to use my constraints here.
So this is circles, it's just the
Yep.
projector makes them oval.
Oh, does it?
Yeah.
That's unfortunate.
If you look from here, it's oval. If you look from down
Oh,
there,
darn it.
Yeah, I think the image is
Yeah.
stretched upward on there.
Different. Yeah, certainly.
Why did you start another sketch? Is
Huh?
there any-
I didn't start another sketch. I chose the
Can
same.
you span sketches on the left? Yeah.
The second
That's
the second sketch should be my my line. Here, let me hide this. So as you can see, this is the only sketch that's active. Run into the sketch again. And then we are going to use our coincident to go here. And then we are going to use our, oh, that's the wrong constraint. Where are you? Again, I moved from SolidWorks. Constraints are,
Can you use another coincidence on the last.
oh yeah, you're absolutely right.
That's-
There we go, cool. So here we are. So it looks like we lost perpendicularity on this construction line here.
I think you have to center that left circle as well into the line.
Which guy? Oh yeah, you're absolutely right. How funny. Good call. Okay, so we lost perpendicularity for some reason on this this line here. So I am going to use our. I think I should be able to go.
I think the one next to it, the one that
Which
is
guy?
on the vertical constraint.
Oh, vertical.
The
Yes.
one next to down one.
Yeah,
Oh, this guy, of
Yes.
course. Let me,
Yes.
perfect. Thank you so much. All right. So here we are. We have the an overall a fidget spinner type device. I think we're going to add some lines here on this sketch plane to connect these. Actually, you know what we need is we need a center hub here. So I'm going to go back and use a center diameter circle. Again, this is C as a shortcut, and I'm going to make sure that we have a little bit of space for our bearing to slide into. 1.25 inches. What? 1.25. There we go. Wonderful. Okay, so now we have our plane here. I'm going to sketch L for line. We're going to go across. Oops. Stop that. L for line again. And now we have something. Oh, I screwed something up there. Sorry about that. There we go. Okay, so I'm going to use a D for dimension, and I'm going to make sure that we are at have a reasonable thickness here. So I'm going to do, I think, 0.3 inches. Oops, 0.3 inches is perfectly fine. And something that I can do actually with the rest of these to constrain this is reference them all to this dimension here. Oops. And I accidentally did that again. And of course, this is not necessarily the best etiquette for constraining a part. Okay, so here we are. We have our fidget spinner type sketch here. This is a two-dimensional sketch. I'm going to now modify it. We're going to extrude this. Actually, before we do that, let's trim some of these extra lines that we don't need here. We're going to use T for trim, obviously. Here we go. Did I get a project line? I don't understand why this happens. Sorry.
Your battery's running pretty low.
Oh, it is. Yep, let me grab my power adapter. Sorry about that. All right.
Do you need to have a big kind of fancy GPU laptop like that? Or it seems like it's pretty simple?
So it's a good question. You don't need to. If you we'll get to where kind of the compute is necessary in just a moment here. I don't know why. So I was running into this issue the other day.
You might want to make sure the end of these lines is, those dots
Yes.
are on the circle.
Yes.
So can you
So we're getting this orange color, which means that they are there, but for some reason here, you know what, I think I did actually make the mistake of creating a second sketch. Yeah, I sure did. Yeah, that's the issue. Sorry. So let's actually delete this sketch here. Stop sketch. All right, let's go back to this sketch. Sorry about that, guys. As you can see, I'm not very used to teaching. In fact, actually cancel. Let's delete this, and let's actually just make a line all the way across. And then another one here. So as you can see, the dimensions might not be perfect here. Actually, I think they did end up perfect. They are equal. Yeah, we actually don't need to constrain this. I'm going to go back to T for trim. I'm going to remove my lines. This is another glitch I've been encountering, that Fusion 360 just leaves this like ghost line, which is really frustrating
It's
to me.
part of the radius
this is just showing you the radius.
diameter.
Right.
Yeah.
So maybe
So
it's-
You'd think that
You
they
can
would just.
rotate- you can rotate the radius line.
Oh, can you?
Like that, yeah, but yeah.
Okay, so I think since we had that second circle, we actually lost our other center circle here. So I'm going to go to 1.25. There we go. And we're going to go back T for trim. We're going to lose these sections here. Stop sketch. And now we have something that looks a little bit more like a fidget spinner. Now, something I was thinking of doing was actually I have a bunch of broken carbide, as you can imagine. And so I was thinking of actually, to get some extra weight in there, taking some of my 3/8" tools that I've broken and inserting them into holes here. So I'm actually going to make a couple 3/8" holes here that I can hammer in some 3/8" carbide. So Fusion 360 and most CAD programs will take a dimension, so I'm just going to type in 3 divided by 8, and then it automatically enters times 1 inch, and there we go. And I'm going to do the same thing on this side. And now I have our holes here. So now we're going to modify our sketch here by extruding it. And I believe it's actually called extrude. It's called press pull in this piece of software. And we're going to go out by, I think, probably a reasonable thickness would be like, what do you think, 1/4 inch? Let's go about 1/3 of an inch, so 0.3 inches. There we go. So we have a fidget spinner body here. Wonderful. So I could go and model in, well, so a few things that I'm noticing here as we cut it is that our tools, since they're round, are actually not going to be able to reach these sharp corners here. So what we're going to go do is we are going to, I think my final profile on this is going to be done, on the outside is going to be done with a 1/4 inch tool. So I'm actually just going to give all of this a 1/4 inch radius. So I'm going to go to modify again, and I'm going to use fillet.
If you were to carve this as is, would you get an error saying that those
No.
corners there are too small for the tool bit?
No. But you will, actually, you know what, let's just show you what that would look like. Let's hop into Cam here. And let's create a new setup, and let's just, I'm going to change this later, but let's create a 2D adaptive clearing with a 1/4 inch tool. Cool, let's do that. And I'm going to select this chain here, and let's see what that generates. So this is a generated toolpath from that, and let's actually go in here to simulate, and let's show the stock. And let's zoom out a bit and change our angle. So I'm going to hit play here, and we will speed this up a little bit. So let's pause it there, go back to front. So as you can see, it actually is just already injecting a chamfer or a fillet right here. So it's kind of unavoidable. It will cut as deep as it can go, right? In fact, I can actually go into my toolpath here and go to my settings, and I should be able to select a, where are you? I may not be able to do that on a 2D adaptive, but there is a minimum minimum radius that it will cut. I generally have it set as default to go for the minimum radius of the tool, because if I go smaller than that, it will try to get in there, and then it will mar your part. It'll change the dimensions from what you want. So we're going to go back into model here, and I'm going to again go back to modify. We're going to do a fillet. And we're going to select all of our kind of corners here. Cool, so now that we have them selected, we can also use rule fillet to automatically select these, but it doesn't always work for me, so I'm sticking with this. So again, with the radius, we're going to do for a 1/4 inch tool, which is not a 2.5 inch or 0.25 inch radius, it's 0.25 divided by 2. There we go. So now we have something that our 1/4 inch tool can cut into. Nice smooth transition. It'll work great. Okay, so now we need to talk about the second model that we're going to develop here, and that is for our little center, where your hand is going to be touching the spinner. So let's create a new design. Again, we're going to create a sketch on the looking down as if we were the spindle. We're going to be on the XY plane here, and we want this to kind of cover the bearing, and we had that at about 0.8. So let's actually do 0.9 inches. That actually might be a bit large. Let's go 0.85 inches. Perfect. We're actually going to start there, and I'm going to modify until it looks right. Obviously, this is not a dimensionally, it doesn't have to be perfect. It's going to be interfacing with your hand, not with the part. Obviously, the diameter that's going to be interfacing with the inside of the bearing has to be spot on. In fact, probably a little bit undersized, so that it can get a nice press fit. So I'm going to extrude this guy, and we're going to go up, I think, 1/4 inch. That might be a little bit too small. Let's actually go to 0.4 inches. So that is slightly smaller than the full width of our stock here. So obviously, the diameter of this is 0.8 inches, which is not going to fit on the inside of our bearing. So we're actually going to modify the surface here to make sure that it does. Now, this is not a good way to measure an accurate bore diameter for something like this. It'll, I think, work for the circumstance, but I forgot my what are they called? They're essentially a transfer tool. You stick them into a bore, you expand them, you pull them out, and then you measure that device as opposed to the bore itself with a very accurate micrometer. Instead, we're using the back of a relatively cheap, not necessarily high precision set of calibers to do this.
Question. The chef is wondering when you should start cooking. How long roughly do you think it'll be?
I think we'll probably be ready to start machining in under half an hour.
Start machining. When do you think you'll finish machining?
Probably by 3.
3. Thank you.
Okay, so we have a 0.3135 allegedly internal diameter on this, and that is going to be the radius that we're going to sketch onto this surface. Again, we're going to use center diameter circle. We're going to point 0.3135, I believe. Yeah, it's pretty close. So we're actually going to go with 0.313. Let's not add that 5/10 in there in case that I'm wrong or my pressure's incorrect. And we're going to move over here. We're actually going to modify, and we're going to measure the thickness of this and divide that by 2. So this is about 3/10 of an inch thick. So let's go 0.3 divided by 2. That should do it. Cool. And I actually screwed that up. As you can see, I did it for first. So I'm going to hit Control Z here. I'm going to modify. I'm going to make sure that I select this. I'm going to go negative 0.3 divided by 2. Wait, negative 0.15. Let's just use our brains here. Okay, so now we have something that looks like a knob. I think that's a little bit tall. So I think I'm actually going to reduce the size of this by, I don't know, whatever the device gives me here, by 1/10 of an inch. Perfect. So I think that this will do it. This is a relatively easy shape to cut. Again, because this is so small and my vice jaws are huge, it's going to be really difficult to get an accurate cut without flinging this thing across the room or breaking a tool or being able to measure and reference it accurately in the machine. So I think the next step to be able to cut this is to actually make a fixture that is going to hold these parts down. So I have some more bar stock in there, and I think what I'm going to do is I'm going to take a piece of that bar stock, cut some square shapes. Actually, I'm going to stick these directly in the vise since they're square. We're going to cut this this profile here of this small diameter with a small flat. Let me actually just start modeling this so you guys can get a better picture of kind of what I'm talking about here. So let's use a 1.5 by 4 inches should be fine. Let's modify this, bring this out by 0.5. I think that's how thick my stock is over there. So the plan here is to create 2.3 inch circles. It doesn't really matter where they are because we're actually going to be modeling this with the part, so we can kind of set them wherever. I'm going to modify these. I'm actually going to send them all the way through the stock here. So now we have two holes. So these are actually going to be sitting in there. And then what I'm going to do on this side is I'm going to drill and tap a couple of holes.
Oh, you can tap?
Well, I'm going to probably hand tap. I could tap in the machine, but I don't have a tension compression head, and I'm worried about breaking the tap. And so let's let's actually measure our screws here. So we have a screw, and the screw head is 0.3. Everything's 0.3 inches, I guess. So let's go 0.31. That should do it.
Is it metric ball bearing screws? Are they metric?
Yes, yes, but we're going imperial. I could obviously measure all this in metric, but it's a lot easier for me personally to think in imperial measurements. I'm actually going to change my stance somewhat on where these are positioned. I'm going to actually turn this body off. I'm going to find my sketch. Wait. I'm going to move these a little closer to the bottom here. Again, none of this is going to be critical. This is just a fixture. Since we're going to be modeling this with the little knobs in it, the machine will know where to go. So not necessarily something that you would want to be a little bit more cautious if you were making an aircraft part, but we're making a fidget spinner, which it's not going to be a big deal, I promise. So let's turn our body back on. We should still have those holes. I'm going to measure the depth of our screw head, because again, well, actually, it may not totally be necessary. But we are, oops, yeah, I didn't need that one anyway. We're going to bring these in by negative 0.15 inches. And then I'm going to create a, I'm going to cheat. I'm going to go back over here. I forgot this. Oh, I do remember the size now, actually. I'm going to create 2 holes in this for a 9/64 drill bit, which is, I'm sorry if you guys, I'm a big fan of metric screws. So this is about a M4 size, about 4 millimeters, which is actually the screws that we're going to be using. So we're, of course, mixing imperial and metric today, which is what NIST does, which is real annoying. NIST, National Institute of Standards and Technology. It's basically the ISO in the US.
How do they mix it?
So a lot of people say, oh, why doesn't America use the metric system? The US does use a metric system. The American people don't use a metric system. So the NIST sets the standard for the inch, but they are using the ISO standards and doing conversions.
So an inch is precisely 2.54 centimeters.
Well, close, not quite precise, but
It's so close that you don't need to measure a difference, usually.
pretty close. So we have on this side of our fixture plate, we're actually going to be tapping an M4 by 70 or by 0.7 screw hole here, and so that we can clamp down on our part that we want to fixture. So it's likely that I'm going to deck this off little by little at the top until we get a really good clamping force. But we don't want the part to rotate. Obviously, we're working with a rotating cutter, and if it's sitting in there and it rotates, we're going to ruin the part. We're going to maybe ruin a cutter if I use a small cutter. So what I'm going to do here is I'm actually going to create a small flat that will interface with that screw. It doesn't need to be big. And I used L for line again, and I'm going to modify this guy, and we're going to just bring it down here. Perfect. So we have a flat. We have our fidget spinner knobs, and now we can start talking about actually creating the CAM, the computer-aided manufacturing, in order to give the machine a toolpath that it can use to cut this out of our material. So we're going to fly over here. We're going to go to Model CAM. I'm actually going to delete this setup. And here's my material. I'm going to take a couple quick measurements of it. I know that it is about 1/4 of an inch thick, but I don't know about how long it is. So we're going to figure that out real quick. 4.19 inches. Is that longer than our, or is that shorter than our overall part?
I think so.
I think you're right. So I might have to cut a new piece of stock here. It's not a big deal. Wait,
Is it measuring between the centers?
it is measuring between the centers.
We did 4.75 over.
We did, yeah. So I'm going to cut a 5-inch piece of stock. It'll be fine. So let's.
Do you have to tell it what? Sorry, do you have to tell it what material? Like it's aluminum. You have to tell it what grade aluminum it is.
The software doesn't care.
Okay.
I care. So so we'll get into that once we actually start building it. So I'm going to go and I'm actually going to create a 2D adaptive clearing, and essentially we are going to. This is where it matters. We're going to get into that. So I'm going to use. I want this to go. Actually, I'm sorry. Let me create a setup first. Let's go to our stock. We're going to do a fixed size box.
I think it told you how big the model is before you switch back to the not fixed size box.
Oh yes, relative size box.
Yes, it told you.
Right.
it's 4.
4.83. So we do need a 5-inch. So I'm going to go to fixed size box. We're going to go 5-inch. The depth is 2 inches, and our Z height is 0.75 inches. None of this is necessarily critical. It's important that the machine knows about what the stock size is, but we have some leeway because it's aluminum and it's not Inconel or titanium or high carbon steel or anything that's going to snap if I'm a little bit wrong. So I think that is a. So we're going to set the origin actually to the top right-hand corner of our stock. And then we're going to hit, I'm going to make sure that my settings are correct.
Flip the y-axis?
Say what?
Will you flip the y-axis or what do you do?
No, that's fine. All right, there we go. So we have our setup here. I'm going to do a 2D, actually I'm going to do a facing operation, and this is actually going to deck material off the top. It's going to give a nice surface finish. And I'm going to, you know what, let's actually do that next. Let me go back into my setup because that reminds me that I need to set where our model is actually sitting here. So as you can see, it's kind of sitting in the middle of the stock. I don't necessarily want it there. I want the outside dimensions to be relatively accurate. So I'm actually going to move this to the top. And I'm going to offset it by 1/10 of an inch. So let's do 0.1. Oops, 0.1. There we go. Let's actually do 0.5. Oh, 0.05. There we go. So we're offset from the top here. As you can see, this is where the machine will know that it's sitting. It's basically going to say drop the Z height down 1/2 of a 10th of an inch or 5/100ths of an inch in order to be able to reach and start cutting the part. So we're going to start with a 2D adaptive clearing of, the tools that I'm going to use. Again, I've preset the proper, what someone might call feeds and speeds for the specific tools to be able to cut aluminum. And
Is that in here or on the controller itself?
in here.
Okay.
So the only thing that the controller cares about is the height of the tool. It doesn't care about diameter. It doesn't care about anything. So I don't even tell it the controller what RPM it's going to be spinning out. This is all happening in the cam. So I'm going to use a 1/4 inch flat end mill. And we are going to select our pockets here. And we're going to start clearing the material. So I'm going to make sure that it's aware of the stock. I'm going to make sure that our coolant's on. We're going to be going full bore here at 10,000 RPM. We're going to be cutting at 42 inches a minute. So with aluminum, more or less, you want to use as much RPM as your machine has. A lot of the very aluminum specific machines that you would see from a company like Datron function as high as 60,000 RPM. Some of them go far beyond that. I mean, there are things that Boeing uses that are robotic arms that are able to make huge aluminum parts that are 180,000 RPM.
Why do they need them that much?
Huh?
Why do they need to go with that fast?
It's kind of all about efficiency. So let's talk about this. So as you can see, at 10,000 RPM, my cutting feed rate is 42 inches a minute. So what that basically means is that my cutter will be moving across the material at 42 inches per every 1 minute. So what kind of sets that 42 inches a minute at 10,000 RPM is this value right here, which is feed per tooth. So this is how far it's feeding with every tooth that's going by the material. So basically my chips are going to be 0.14 or 1.4 thousandths of an inch across at their widest point. So as you can see,
With aluminum in particular, since it has such a low melting point, do you ever worry about the tool getting too hot, or is it moving too fast for that?
so it's not a concern.
Your tools.
Right. So when you start worrying about things heating up is when you're not taking a deep enough cut. So you want the heat from the cutting process to be going into that chip and moving away from the part. So it's kind of like how firearms work. How firearms keep cool is that they're ejecting a piece of hot brass, right? That hot brass is carrying heat away from the gun and keeping it cool. This is the same way. You're taking a cut, you're putting a lot of friction into the chip, and then you're moving the chip away where it can vent basically that heat to atmosphere, and not to the part, not to your cutter. So you can cut dry at this feed rate and not have the part or the cutter heat up in the slightest. But it's always good to have the backup of coolant because you can ultimately make your tools last longer. So a lot of people, a mistake that they make when they first start doing any kind of machining, whether it's on a manual machine or on a CNC machine, is they take very light cuts. And the problem with light cuts is that they have kind of a burnishing effect against the material. They don't actually dig in. They will deflect and float on top of the material, and that's how you burn tools out. So we're making a real chip here. We're cutting 1,000th thickness chips, which...
So you can burn the tool even with a coolant?
Yeah, absolutely. You can completely ruin a tool, especially carbide tools. High-speed steel is a little more forgiving, but...
Because you're not cutting deep enough?
Right. It's a little counterintuitive. So when you're cutting things like titanium, everybody says, oh, titanium's this really hard, impossible metal to cut. If you cut titanium on a manual mill, you'll notice that it gets very difficult very quickly. Titanium is very susceptible to something called work hardening. So when it heats up or when it's impacted, it will get significantly harder. So the way that you cut aluminum effectively is by taking a very aggressive cut, not a light cut.
Aluminum or titanium?
Titanium. Aluminum tends to not work harden very badly. It's possible, especially outside of the 60-61 grades. 70-75 has a lot of zinc in it. It cuts very differently. It changes a little bit in its grain structure when you're cutting it. So it's a little bit, it gets a little bit strange. So 60-61 will have no problem. We're going to run this thing as fast as we should run it. Actually, I could take a little bit more of an aggressive cut, but it's probably not going to be worth it because I think that this is not going to take a very long time anyway.
Does the RPM depend somehow on the diameter of the tool?
Right. So that is a interesting question. So that value right here is surface speed. So this is just about going to be a constant value. So a lot of people will say how many if you talk to a machinist, they'll say how many surface feed you're running, or what's your feed per tooth. Those are generally the two values. They're sort of related. So this surface speed is essentially that quarter diameter tool. If it were a wheel and it were moving across the part, how fast would it be moving? And that is 654 feet per minute, so very fast.
So it looks like those are redundant. So
yeah, so it does the calculation. So if I go in here and I change this to 0.1, if I change my feed per tooth to 0.19, it will change my cutting feed rate.
Oh,
to 57 inches a minute. But the surface speed is a function of the diameter of the tool and the RPM, or the circumference of the tool and the RPM, right? So this will stay constant as long as the RPM and the diameter are constant. So I'm going to take this back down to 1.14 because I don't want to snap my tool. And let's go back to our cam here. So I think that, okay, so this right here, this is basically telling, this will be telling the machine kind of where the top and bottom of the part are, or how deep the cut is going to be. So as you can see, the top height, which you see is this this blue guy right here, is showing right at the the top plane of this part. So I actually want the bottom height. Oh, this is actually fine the way it is, so we don't need to change any of this. Let's go to our passes. So tolerance, this is 4 thousandths. I think that's perfectly fine. I'm going to turn on smoothing. So what smoothing does is it essentially enables the, actually, I'll show you guys what it means once we create the cam. So stock to leave is a feature that is in Fusion 360 CAM and many other CAM softwares. And what stock to leave basically says is that I'm not going to cut all of the material right down to the surface of what the end part's going to be. I'm going to leave a certain amount of stock so that I can go back and make a finishing pass and end up with a good surface finish with low tool deflection. Adaptive clearing strategies have put a lot of pressure on the tool and deflect the tool quite a bit because they're very aggressive. They're about as aggressive as the material can take at a specific feed rate. I mean, it's basically an ideal scenario for as hard of a cut as you can take. So they're not necessarily going to give you an accurate dimension. They're going to clear out a ton of material in a short period of time. We're going to do some other. We're going to make some other strategies in order to ensure that we have a dimensionally stable part at the end of the game here. So I'm actually going to turn off axial stock to leave. So radial is obviously, everything is kind of relative to the cutter. So radial stock to leave is how much stock relative to the radius of the cutter. Axial stock to leave is how much is relative to the axis of the cutter. So we don't need any axial stock to leave, so I'm just going to change that to 0. In fact, yep, let's change that to 0. That's perfectly fine. I do want to do this. This is 0.4 inches. I can actually take that in one cut, but it'd probably be more fun if I did that in 2 cuts. So let's do that in 0.2 inch step downs. Linking. So
did it change your part on the inside radius when it knows how big the tool,
it will never change the part.
It never changes the part, but you're not going to have sharp angles when the circle comes into the flat spot. You're going to have a rounded.
Right. Yeah. So I when I made the fillets in the model.
Okay.
Yeah. So the part will always show me essentially what I created. So okay. So we have our retraction policy. So full retraction is basically something that you might use if you were being ultra careful. If you had a fixture plate or some bolts or some other clamps that were hanging around, you would use full retraction to prevent your cutter from crashing into those things. But we're not going to have any of that, so I'm going to use minimum retraction, which is going to speed up it's going to lower the amount of motion control that the CNC machine has to do, and it's going to speed up essentially the manufacturing of the part. So I'm going to turn up our no engagement feed rate, which is basically the feed rate that the cutter is going to take when it is not engaged with material. I'm going to change that to the maximum my machine can go. Actually, let's cool it. Let's go a little bit less. Let's do 90 inches a minute. And let's see what kind of tool path we came up with. So these are always the cool tool paths. We're going to do a helical ramp. And as you can see, I had set it to cut multiple holes, but it's only cutting one. So The cam is smart. The cam knows that I've made a couple choices in my settings that will prevent it from kind of making a cut into one of these smaller diameter holes. But I want to make those cuts, so I'm actually going to go over to my linking again. I'm going to change my helical ramp. I'm actually going to increase that to 5 degrees, and that is how quickly essentially it's going to ramp. The ramp taper angle, that's fine. So the minimum ramp diameter right now is 0.2375 inches. So that's smaller than these 3/8 inch. Wait, then why isn't it doing it? That's very interesting. Minimum ramp diameter. I don't know why it wouldn't be doing that. Maybe I didn't select those pockets. I sure did. Very interesting.
Is the ramp diameter does that include the tool's diameter? Or is that only the center?
That is the center line of the tool, and that's I think you actually have a point there. So let's actually go to 0.1. Let's do a minimum. Actually, let's do.
Maybe use plunge just to see if it will pick up the.
Say what?
Do you want to use plunge just to see if it will pick up the other holes?
Yeah, it certainly will if I hit plunge. So yeah, let's take a look here. Yeah, so as you can see, it will plunge in, so it is picking up the other tools, which means that it is a ramp diameter problem. So let me go back to helical, 5 degrees, and I'm actually going to reduce this to the minimum to 0.1, and let's see what it does now. Still too big, so let's make it even smaller. You know what? Actually, let's cancel these. Let's do a drilling operation. I do have a 3/8 inch drill. This. Let's actually just do this pocket here. Cool. Awesome. All right. So this is going to be sitting in a 0.75 inch piece of stock. And I am going to want some reference geometry later that I can use when I flip the part and deck off the rest of the material. So I'm actually going to drive this hole all the way through, and I'm going to actually use our bottom height, and I'm going to use stock bottom minus 1, let's do 0.05. Cool. So that's going to change our toolpath a little bit, and as you can see, it's cutting through stuff that isn't being modeled. So if I go here and go to simulate, you'll see that it is going to be cutting through stuff that exists though. So we have our adaptive clearing. Let's actually do a drilling operation here. And let's choose 2 holes. And let's do a pre-drill first with a 9/64 inch drill bit because we have it handy. And the type of drilling operation we're going to do, actually we're going to adjust the heights a little bit. We're going to make sure that the feed height is from stock top plus 0.2 inches. And the feed height is essentially where it's going to start its cut, and that actually looks incorrect. So let's actually go 0.3. Feed height. Oh, that is the retract height. Oops. Let's cancel that. Let's create.
How are you holding this to the bed?
This is going to be on a vise.
It is, okay.
Yes. Sorry, let me select my tool again here. Geometry. So I don't want to change my retract height for some reason. I want to change my feed height from stock top plus 0.2. So, and I do need to select the holes I want to drill. And I'm going to drill tip through bottom, make sure that we are leaving, and let's actually break through at 0.2. There we go. And then cycle, I'm actually going to change this to a deep drilling full retract. This is not a deep hole. I just don't want to break a bit. It's a smaller bit. I am going to be pushing it pretty hard at a more or less, this is a new drill bit, so at a completely untested feed rate. So I'm going to take it a little bit easy. And then let's just set a dwell at the bottom to make sure that we are breaking our chip at 0.1 seconds. So
this is an actual drill bit and not an end mill on this one?
no, this is a drill bit. So some situations that you might want to use a drill bit instead of an end mill is that drill bits are very axially stable. They don't deflect very much axially, so they're capable of removing a huge amount of material really quickly. So say you were trying to make a honeycomb structure. If you took an end mill in there and you're removing maybe 1 cubic inch a minute of material, it's going to take forever to do that. Whereas a drill bit might be able to remove on this machine 6 cubic inches of material a minute. So you would just wrap it out all of those holes and then clean them up with an end mill and ultimately end up with, you know, a tool path that was 10 minutes as opposed to several hours.
So for this one, you have separate parameters where you set your drill feed and speed based on
Right.
your chip depth or your
Absolutely. So let's take a look at actually what I have set for this specific drill. So this is going to be spinning at 8,148 RPM. Again, that's about 300 surface feet a minute. That's the surface speed. That's generally recommended 200 to 300 surface feet a minute for aluminum. And then the plunge feed rate is going to be 32.5 inches a minute. So nearly as fast as we're milling is how fast we're going to be drilling, which is pretty quick. And then the amount of feed per revolution, the chip size is going to be 0.4 or 4 thousandths of an inch, which is almost 4 times what we're milling at. So significantly higher material removal rate. Granted, it's a smaller diameter, but you can cut it at that feed per revolution with a 3/8 inch tool as well and get just absurd material removal rates.
They usually shoot about 7 thou chip load on aluminum stuff, so your 4 thou is probably pretty safe there.
Right. Yeah. So this is a small drill.
Yeah.
And then I only have 1.5 horsepower, not 15. So 7. I could probably do 7 on a slightly larger drill, but I'm gonna stick to 4. Okay, so now I'm going to do another drilling op. I'm actually going to duplicate this drill op.
It's a 1.5 horsepower because you just have 120 volts in there. That's all this is. Or is it a full 240 volt?
You can run on either.
Okay.
I may be swapping that spindle for a 3 kilowatt spindle. We'll see. 3.5 kilowatt spindle, 60,000 RPM spindle. Not that I need it, but I want it. But I'm trying to figure out kind of how the black magic has to happen in order for that to kind of work out. So I'm going to duplicate this. Again, this is the same op. All I'm going to do here is I'm going to change the drill I'm going to be using. So I'm going to select a, you know what? I just realized that I actually don't have a 3/8 inch drill. Let me just make one. So I'm going to create a new tool here, and we're going to go to our cutter. We're going to select a, where are you? There's my drill. 2 flutes, high-speed steel, no through coolant, I wish, and then we're going to do a 3/8 inch. Cool. I technically should go measure my drill bit and make sure that the software knows, because it can do some kind of crash detection, but I do like to live a little bit dangerously. So I'm going to set this tool number as tool 32. And this is something that I'm going to obviously set in there. And then let's change that surface speed to, I think 300's reasonable. See, this is a heavy cut, right? You mentioned you were cutting at 7 thousandths. This is cutting at 12 thousandths. So I'm going to reduce that to less. Let's stick with 4. Let's see how that goes.
I think it's a 0.40.
Oh, fun. Yeah, that's way too big. 004. Thank you for catching that. Would have been fun to watch.
Does it calculate the extra breakout depth automatically based on the tool geometry, or do you have to make sure you go further to get full diameter and get the tip all the way through the back end?
So, ask me again.
So on these, you're doing a full hole all the way through.
Right.
And your tip's got that angle to it on the drill
Right.
bit. Does it already calculate that based on the drill diameter?
Yes.
The angle, and add that depth automatically, or do you have to add that extra breakout depth yourself?
No, it will. The software does that. I'm going to make it go a little further though, because obviously there's a burr at the bottom of every drilled hole, and so I don't want that to be there, or at least I don't want it to mess up my dimensions. So without having to go in and deburr it and whatnot. So go back in here. That's a heavy cut. All right. Let's see how it goes. Again, we're going to do deep drilling with a full retract. Pecking depth is about 1/10 of an inch. I think that's reasonable. Let's actually go. Let's go a little higher than that. Let's actually just do 1/10 of an inch. It's not that much higher, but makes a difference. Okay, dwell before retract. Cool. All right, so again, that's basically the same tool path, so let's make sure that we're getting all the way through. Wonderful. So let's actually run a simulation real quick and start our cut. As you can see, stock is on. So we are seeing essentially what we would be seeing in the machine, except my aluminum's silver. So I'm going to speed this up a little bit to make sure that we're not getting any weird crashing. Good.
Why does it move several times since it's the same hole?
Just to clear chips out. Deep holes, pockets of any kind, generally have, it's problematic to kind of extract chips from it. Big machines use high pressure coolant. I use an air blast that missed. And so it should be able to clear the chips out just fine, but it's not something I want to risk. I just want to have a successful part at the end of this. So I probably could do it in one go, but and also safety is an issue when you're making kind of blind calculations on what you think the feeds and speeds should be. You can end up with really long, sharp, dangerous chips that can be flying around. If I need to go in there with a pair of pliers while the machine's spinning and yank it off, I would do that in my personal time, but I don't want to get my arm ripped off during a demo. So I'm gonna not do that here. So again, this is just so that we can be successful in our endeavor here.
I didn't look at the machine. Does it stop for tool changes?
Yes.
Tells you to put on.
I hope it does. Yeah, no, of course it does.
Okay.
Yeah.
It's gonna be real quick.
Certainly, yeah. It will stop, yeah.
Well,
It will, yeah, it'll stop, it'll say insert this tool, and then let you continue. I'm waiting on my automatic tool changer right now, but at some point it'll be here.
Does the software have any kind of built-in value safety guards? Like you can put in, like if you fat finger something,
It will do whatever you fat fingered, generally speaking. It'll do whatever you fat finger within the capability of the machine. That's why the simulation is important. That's why paying attention where your hands are is important. And so, again, it's dumb. Once it gets from here to the machine and you hit cycle start, it's too late. I mean, you can stop the machine certainly, and hopefully you can stop it before a crash or before an injury. But it's very important to make sure and have as many kinks worked out beforehand as possible.
So it's more dangerous and less forgiving than 3D printing.
Oh yeah, certainly. I mean, you might get burnt a little bit with a 3D printer, or with an SLS, blind yourself permanently, but it won't rip your arm off. Okay, so we have our internal pockets. Let's actually get a profile done here. Let's do our 2D adaptive clearing, and let's actually do the outside profile here. We're going to make sure that it's aware of the stock. We're going to use our 1/4 inch coated. Actually, let's step up. Let's use a little bit bigger of a tool. Let's use the shear hog. And I was actually going to make a recommendation that you emulate your tool geometry here based off of that shear hog. So the shear hog is a 3/4 inch aluminum tool. Can remove a ton of material. I think I have it up to almost 6 cubic centimeters or cubic inches a minute, which is a pretty high material removal rate on that machine. It's about as high as I was saying you could get out of a drill bit in this machine. But it's 3/4 inch tool. It's very large. You can't necessarily fit it in every pocket. You wouldn't necessarily want to. It's also very loud, and the inserts are super expensive. So again, it's running at 10,000 RPM. And again, when you hit this thing, it probably weighs close to 7 to 8 ounces, spinning at 10,000 RPM. You don't want that thing detaching. So a lot of mass going really fast. Yeah, you'll see it. I love the tool. I think it's great. So we're going to go down to the floor here, heights, clearance height, top height, stock top. So this is all, again, I don't want any stock to leave. Let's do 0 axial stock to leave. Let's keep our radial stock to leave. We don't need to do any sort of ramping. It's unnecessary because we're cutting on the outside of the part here. So let's see what kind of toolpath we get. So as you can see, this is a relatively typical adaptive clearing toolpath. You can see that some things on it might not look very intuitive, like why doesn't it cut in a straight line, or why doesn't it follow the profile? And the reason why is that it is actually trying to maintain a constant load on the tool, and let's actually change this. So optimal load is basically how much of the diameter of the cutter is engaged with the material at any given time, and I'm actually going to change this to 20%, so 0.75 times 0.2. Wait, what? Oh, not times 2, times 0.2. There we go. Wonderful. And I'm actually going to do the same thing on our first adaptive. 0.25 times 0.2. And as you can see, that actually changed our toolpath by quite a bit. It actually tightened it up. So not that I would have broken a tool on the other one. This is just going to have a little bit less tool deflection. It's going to be able to run a little bit quicker. And as you can see, we added a few more paths here in this area. Oops. With this 3/4 inch tool. So
I'm still a little confused how you're going to vice it in there. You're going to have that big of an angle. Is the stock deeper? Is that how you're vicing?
The stock is deeper, yes. And then, yeah, we're basically just going to deck the remainder of the stock off. And we'll talk about how it's going to end up getting viced up. All right, so we have these adaptive strategies. Again, like I said, they are not meant to be finishing strategies. So what we're going to do here is we're going to make sure that the part is pretty when we're done with it. And I'm going to do 2 operations called 2D contour. And actually, I can do those contours all in one here. And what a 2D contour essentially is doing is it's forcing the edge of the tool to follow the line that I select. So again, it is super dumb. If these 2D contours were existed before these adaptive clearing strategies, it would snap the tool because it would just crash into way too much material. So I'm going to make sure that we have our heights correct. We're not going to do multiple depths. It's fine the way it is. Cool. All right. And this is a very simple toolpath. Again, this is just walking around. And I selected the wrong tool. Let's do our 1/4 inch tool. And that's going to leave a nice surface finish on the inside and on the outside of the part. Let's make sure that I'm not linking anywhere like through material that I want to keep. Wonderful. Okay, so we have our first adaptive. We have our deep drilling operations. We have our 2D adaptive clearing. We have our 2D contour. And now let's add a facing operation. And the tool that we're going to select for this is called the Superfly. And this is a fly cutter. Doesn't look like it doesn't look like how it's modeled. It was actually the tool that was sitting in the spindle, and that runs at a significantly lower RPM, 2,500 RPM. And because of the diameter is so large, it's running at 1,800 surface feet a minute, so much faster if it were a wheel traveling across the part. But it's running at a slower feed rate, which is 16 inches a minute versus 40, so a little more than half. This thing is also capable of removing a tremendous amount of material, but what it's really great at is making a great surface finish. It'll be shiny like a mirror once this passes over it.
Does that use inserts?
It does. It is a polished carbide insert cutter. So there we go. That's our facing operation, just one line, and that will go down to the very surface of our part. And now to make it pretty, we're going to do a chamfer. So we can go and we can model a chamfer. Actually, let's just do that real quick. It's not necessarily, personally, I don't like modeling chamfers. I think that it's a waste of time. But let's go model this chamfer. So what we do here is, I don't know, like that. So this is essentially a chamfer. It's going to walk around the entire outside of the part. This would be a 5/100ths of an inch sized chamfer. I think that that's probably suitable. I'm going to hit cancel. I don't like modeling it. I like cutting them. I think that it's kind of unnecessary, and it can kind of mess with the model in ways that it just simply doesn't need to be modeled. So I'm going to select our tool. I'm going to make sure that I am going to use our chamfer mill. There we go. I'm going to select this chain. Passes, tolerance, finishing overlap, chamfer width, 0.4 inches. I think that's perfectly fine. Linking, wonderful. So I'm going to make sure that I actually have all of our chains selected. Perfect. Got it. So this is again just my 1/4 inch chamfer mill, and it's going to be walking around the part, making that 0.4 inch cut to break that edge, because this will actually be pretty darn close to razor sharp when it comes off after that facing operation. We don't want anybody to hurt themselves, although maybe fidget spinners should hurt people. So this should just about do it. I think probably what I'm going to do, I'm going to go talk to Hats real quick. I'm going to see where he is with the barbecue. I don't want to keep anybody from eating. I'm going to continue modeling our fixture and our knobs, and anybody who cares to join. I don't want to force anybody to sit in here who doesn't want to if you want to go eat. So I'm going to go see kind of where they are on that, and then I think we can start cutting this part here, and then setting up for our second operation. So I will be right back. Give me a couple seconds. Let me make sure we are good. All right, I'll be right back. Oh.